cloud. Okay. So, okay, so I'm going to work some of these. These are going to be off of the old homework assignment, and all of these are about test caliber problems. And so I'm going to work some momentum problems out of, I guess it's homework 11 from old homework assignments. And obviously the first two are going to be off because those come from a textbook that we no longer use, which makes me sad. I really like that textbook, but this textbook might be better. Anyway, so I'm going to go down and do number 5, just because it's going to kind of get us in the like the mood or whatever of momentum. Before I continue, the test will be a week from Tuesday. I think it's the 20th. So I went ahead and put a little link to it in Moodle. I would have liked to do it a week from today, but a week from today I won't be able to do this problem solving session because I have to go get my second COVID shot, which is going to make me really excited because after that I can feel safe going to campus, and that was just going to be really wonderful. Especially because some of you guys would probably prefer to talk to me in person than over, Zoom. So anyway, okay. So the question for number 5 is that there's some sort of black box. Okay. And this is usually kind of like a beginner momentum problem. And I would give something like this on a test if all the other problems are really hard. So this would be like an easy momentum one. But it does have a lot of signs that you have to consider. So what force is required to hold this black box in place if gravitational forces are neglected? So gravity does not exist, or gravity equals 0. Okay, and if the liquid specific gravity is 2.0, so SF is 2. Okay, and so they give us directions here. They say this is the Y direction and this is the X direction. Which is always better when I give you those, because then I know, then we're all on the same page. Okay. And it's got like 4, tubes going into it. And it tells us that they're all jets. And so that's an important thing. So when we see jets, that means it's all open to the atmosphere. So this is entering here, and it says Q equals, 0.30 cubic meters per second. And V equals 30 meters per second. So that's, 30 meters per second, that's rolling. That's really fast. So just to give you an idea, if ever you're wondering, if you're ever thinking about things, you're like, what's 1 meter per second? Obviously we can picture something that's going every second travels a meter, but like, what does that mean for a liquid? And I think the easiest way to think about that is to say, like if you go to a mountain creek, okay, mountain creeks generally move at about 1 meter per second. Okay, if you go to a lowland river like the Mississippi River, it's probably moving at about half that, at least down here. I don't know if that's exactly true, but that's more or less the right kind of scale for that. 15 meters per second. And this one right here, it's got an arrow going up of 0.10 cubic meters per second. That's, Q. And V equals 20 meters per second. Okay, the first thing that should scream to you, so required, we want to know the force to anchor this thing in place. Okay, anchor the box. Okay, for the box. So basically this box is going to, want to go somewhere, and we don't know where it is. Now, the first thing that should scream out to you, like when you're looking at all the givens, is notice that for this one, we've got Q and V. For this one, we've got Q and B. For this one, we've got Q and B. And for this one, we've only got V. So it seems like we're going to want this Q here. I'm going to leave space for that in case. If you've worked enough momentum problems, we're going to need that. But for you guys, you may not know that just yet. So, so here, so like a lot of times when I work these problems, I'll kind of like fold my paper down the middle, or I'll kind of box off a little area for the asides, for like, I got a certain way into this problem. I realized I needed something. So anyway, so let's go ahead and do this. We're going to do the X direction first. And so the momentum equation can be written as sum of the forces in the X plus the sum of the momentum fluxes, which is rho Vx Q. Okay, that's in, equals the sum of the outs, rho Vx Q. Okay, and we always want to remember with these that the Vx and the forces are vectors. Okay, so they've got a sign. Okay, the Q's don't, nothing else has a sign. The Q does not have a sign. Okay, and that's important to always remember. So in this case, in the X direction, we know all the Q's. Okay, that means we're not going to worry about all this vertical stuff. So, we're not going to worry about this, and we're not going to worry about that. We're only going to worry about the verticals. I mean, the horizontals. So, let's see. So we're going to kind of make this a free body diagram. We're going to say there's a force right here. Okay, in the X direction. So that's going to be F anchor X. And so sorry, I should have drawn my control volume first. Here's my control volume. Okay, and actually I should be drawing this just barely on the outside of the box. Okay, and the reason that I'm choosing to go on the outside is because I'm looking for the anchoring force, which is the force on the box. Okay, and the nice thing about that is that means that, oh, I messed up, didn't I, a little bit? Sorry, it actually goes like this. Okay, and the reason that I drew it on the outside of the box is because I want to know a force that is on the box. So this F anchoring force is on the box. Okay, but that whole control volume, it includes the water. So I need to consider forces here. Okay, pressure forces. These are very common to include. Okay, or I'm showing you all the ones that we always need to think about. Okay, so this is going to be PA over here, and then there's a PA over here, and there's a PA over here. Now, in this case, those are all going to go away because of the fact that these are jets. Okay, and this is like key language that you need to look for. If it says it's a jet, that means it's going out into the atmosphere, it's coming from the atmosphere, which means, so the thing we read from that is that pressure equals 0 if there's a jet. Okay, so, just be careful there, because obviously, all 4 openings don't have to be jets. One of them could be going into a piping system or whatever, and so it could be pressurized. And so you just need to make sure to think about whether or not something is open to the atmosphere or not. But in this case, they tell you all 4 of these are jets. Okay, so once we've kind of ascertained that, we've got this one external force. These forces all go away. The other force that we typically think about is we think about gravity. But in this case, of course, it said neglect gravity. So really there should be a weight right here, a weight. Okay, and there should also be an F anchor in the Y direction, which this green color is really terrible. I should not have chosen it. Okay, so that's, hold on, let me change screen so I can see how this looks to you guys. Okay, that's okay at best. All right, so we'll do our sum of forces, okay, in the X direction. And so we've got F anchor in the X direction. We don't have any pressures because these are all jets, and we don't have any weight because this is the X direction. And even if we were in the Y direction, it told us to neglect the weight. Okay, so those are all the forces. Okay, so now we got to do the ins and the outs. Okay, we've got an in right here. So let's go ahead and do that. There's only one. Oh no, they're both ends, right? These are both ends. Okay, so let's go ahead and do that. Let's see. So rho, which is going to be the S of the fluid times the rho of water. That's the gamma of the fluid. Okay. Times Vx. So this first one, Vx is 30. Okay, and I always like to put a positive sign on it because it reminds me that I've accounted for the, let's just call that V1, or let's go ahead and put numbers in here. Okay, so the rho of the fluid is 2.0. Okay, the density of water. Okay, hopefully you guys have memorized the density of water now. It's 1.94 slugs per cubic foot. If you haven't memorized it, make sure you write it down so it's in front of you somewhere in case you need it, so that you don't accidentally put 62.4 or 9810 or 1000 or who knows what other numbers can show up here. Okay, and then the Q, remember Q does not have a sign, so it's going to be 0.30 cubic meters per second. Okay. Okay, so then we'll go ahead and do the out force. Rocky, I love you. You're a very good dog. We just went on a 2-hour walk. It's time for you to take a nap. See your bed? You go lay down there. Sorry, my dog is annoying me right now. Okay, so so then for outs, We don't have an out. Sorry, we don't have any outs. Okay, so let's make this plus. Okay, so then we've got the one on the left-hand side. And so that's 2.0. So we're going to do the rho. 2.0 times the density of water, 1.94 slugs per cubic feet. Oops, that's right, slugs per cubic foot. Okay, and then we've got the velocity of this one. The velocity of this one is a negative 30 meters per second. I mean, that's really a lot of velocity. I guess the beauty of writing these problems is you could just make up whatever you want. Maybe that happens a lot in oil rigs. I don't know, or like industrial settings. I have no idea. And then we'll use the Q, which is 0.30, 0.30 cubic meters per second. Okay. And then that equals, we have no outs in the X direction, so this is 0. Okay, hopefully it should be clear to you at this point that I don't even need a calculator because this and this are the exact opposite of each other. So they're going to cancel each other out. So the F anchor in the X direction equals 0. So yeah, so that's how we solve that one. Any questions about the X direction? Okay, cool. So we will erase this one and we will do the Y direction. Okay, and I'm just going to kind of leave that equation above me. Try not to erase that line. I might get it. Okay. Okay, and let's erase the X's if we can do that.
Dr.
Yes,
Wagner.
sir. Yes, sir.
If the second entry, the velocity going to negative direction, why you say the velocity is like going to the left? So why would it be like plus, like rho and that B and per K? I thought it would be minus because the velocity going that way. That means the water going into the.
Yeah, did I not put a negative sign on it?
Yeah, you put negative sign on the velocity, but not on the.
Oh, on the flow rate?
Yeah.
Oh, so the flow rate is always, this is a scalar and this is a scalar, so it's always positive.
Okay.
Okay, so these two are scalars. So basically the things that I put arrows on, those are the vectors. So the Y, you know, the forces, the V and the Vy are the only vectors in this equation. Okay. There is another way to do it where the Q is a vector, but I didn't do that way because it just ends up with too many signs all over the place. I think it's easier to not have to think about all that. So just make sure you get the velocity right and then everything else is positive. Okay, to me, that's the way that makes the most sense.
All right, we good.
Okay, so then we're gonna do the vertical. And let's see here. So we've got F anchor in the Y. F anchor in the Y. Okay, we have a weight, but the weight is 0 because we neglect gravity. So we're not going to worry about that. We've got pressures, but you know, these are jets. So the pressures are 0. So we're not going to worry about those. Okay, but in general, you might have to deal with those. So just be aware of them. And then let's see, we've got, these are both outs. So we have no ins. So we'll say equals. And then let's see, so we'll do this top one first. Obviously, this has gotten a little bit messy, but we're gonna go, okay, so I need the rho. So it's gonna be 2.0 times the rho of water, 1.94 slugs per foot cubed. Okay, times the velocity in the Y. So this velocity is up, so it's gonna be a plus 20 meters per second. And then times Q. And Q is always positive, so 0.10 cubic meters per second. Okay. And then I've got another term, which is the one coming from this thing right here. So we'll go ahead and say plus, okay, because that's for the summation. So the rho is 2.0 times 1.94 slugs per cubic foot. Okay, the velocity is given as 15 meters per second, but that's downwards. So negative 15 meters per second. And then we need the Q at that location, which we don't know. Okay, that was kind of what I was alluding to right here. So we need to get that. Usually if you need a Q, we need to do continuity. So basically the mass that goes in, so that's going to be the mass that goes in here and here. has to equal the mass that leaves here and here. As long as, as long as nothing is accumulating in here. Okay, so I'd like to do that as in equals out plus accumulation. And what's accumulating in the black box is nothing. Okay, so the in is rho, I guess we could call this 1, 2, 3, this will be 4. Okay, so it'll be row 1. I mean, they all have the same row, but row 1, Q1 plus row 2, Q2. Okay, this is mass flow rate in equals the mass flow rate out, row 3, Q3 plus row 4, Q4. Okay, so let's see. The rows are all the same, so I could turn those all into 2.0 times 1.94, but I'm not going to. I'm just going to say that they all cancel out. Okay, so then I can plug in Q1, which is 0.30 cubic meters per second. Again, common error is if I write CMS on a test, people think, oh, well, that's centimeters per second. Well, it's not. CMS is cubic meters per second. Centimeters per second would look like this. Okay, so this is not the same as cubic meters per second. So just, usually if you pay attention, you recognize that this is a Q. Well, Q has to be cubic meters. Okay, so then we got number 2 is 0.30 cubic meters per second. And then Q3, so this is an out. Where was 3? 3 is up top. So that's 0.10 cubic meters per second plus Q4, which is down here. And that is the one we're looking for. Okay, so luckily this is such a case that really, like, once you get used to this, you could have just looked at this and just said, oh, wait, 0.6 is flowing in from these two spots. So that means 0.6 needs to leave, but there's 0.1 leaving here. So what's going down here has to be 0.50 cubic meters per second. Okay, so we can put that in right there, 0.50 cubic meters per second. Note that in the vertical, this is not symmetric. Like in the X, we had the exact same thing happening here as here. So the force was going to be 0. But in the vertical, it's not the case. So we're not going to get a 0 force. So F anchor and the Y equals whatever the math says this is. So let's see what this is. 2 times 1.94, open parentheses. Let's put times in there. Times open parentheses, 20 times 0.1 plus negative 15 times 0.5. Okay, so I'm getting negative 213.4. And let's check our units. Let's see here, cubic feet right here, cancels cubic feet there. I'm left with slugs, meters. Oh no. How did you guys let me do this? I even talked to you guys about using the correct units for this. Oh no. That is a disaster. Okay. Okay, this is why we check our units. Okay. Right, we're using meters, so this needs to be 1,000 kilograms. It didn't matter in the X direction, so I don't have to go redo that one because it would be 0 either way. 1,000 kilograms per meter cubed. Okay, so now the meters cubed cancels with the meters cubed. Okay, and I'm left with kilograms meters per second squared because we got 2 seconds. So that means that's a Newton. Okay, so let's go ahead and redo this calculation. Okay, I actually like it when I make those errors because it helps me to, I feel like it's good for me to remind, to remind myself and to remind you guys. I don't want to act like like it's so common that, like I don't do it on purpose or something. I make those mistakes. We all make those mistakes. So this is negative 11,000 newtons. And if I wanted 3 sig figs, I would say it's negative 11.0 kilonewtons. Okay. So, yeah, that's it. So in some ways, this should be, so what this means, and the way that I like to think about this is, think about this as like a rocket, so you've got a rocket like this normally, right? So what's happening with the rocket, right? It's expelling a whole bunch of stuff is coming out of its bottom end. And because of that, it's moving upwards, right? Because basically, as it pushes down on that stuff pushes up on it, and so it flies away. Now imagine you were to try to keep this rocket in place. Well, you would have to like hold it. So let's suppose you put a clamp right here to hold the rocket where it was. Okay. Well, if it's expelling stuff downwards, you imagine that that clamp is having the net effect of pushing downwards on the rocket. So this would be the force to anchor the rocket. If I, you know, so in this case, we've got two rockets, right? We've got this thing, and it's got a rocket down this way and a rocket this way. So depending on which rocket is stronger is going to determine which way this force is going to go. Well, if you look at this one, the bottom one, it's got a V of 15 meters per second, which is not quite as big as this one, right? But it's expelling 5 times as much material. Okay, so the net effect is that this rocket is stronger than this rocket. Okay, so you have to push, you have to hold it downwards. That's why we got that negative sign. Okay, so that's kind of a way to think about that. At least that's how I think about it. Okay, so any questions on this one? By the way, this analogy is actually perfect. That this rocket, it works on the momentum equation. I mean, by the way, when people ask you, what do you study? You can say, in fluid mechanics, we are doing rocket science. Okay, I mean, we haven't, this is like, we're not really directing our study in the direction of rockets, but all this stuff, if you guys wanted to go work on work for NASA and work on rockets, this would be the first step. So just something to kind of think about. Not really my not really my direction to study, but I do think it's cool. So anyway, so I'm going to clear this drawing and let's find another one. Let's see. Okay, so I know which one I want to do. So this one I really love. I asked my class this one, and it got kind of interesting. So I'm going to go to the number 9 here because it's a sluice gate. So this is a very civil engineering-y problem because we build sluice gates. Most of us haven't heard of a sluice gate. So it says, consider the sluice gate below. So there's 2 sluice gates, and basically, so you probably haven't heard of a sluice gate. But a sluice gate basically, and is the right drawing, there's 2 drawings of this. So here's the drawing on the right. And it's like, okay, there's some water here, and then there's some water coming out here. And so basically what's going on here is this gate was put here, usually to raise the water over here. And, but, like there's a river or something flowing in here. Maybe this is a river or something. Okay, but we're not going to worry about that. It's going to, basically to us, it's just going to look like a lake. And what happens is, I guess it'll look like a river. Anyway, and what happens is the water flows out the bottom side. Okay, so maybe you put a turbine here because you want to get power out of this thing. Okay, that's a possibility. There's a lot of things that could happen here, but this is what a sluice gate is. And until I took these classes, I'd never heard of a sluice gate. And probably for some of you guys, you haven't either. It looks like we're using the English system of units, which we really should call the American system because we use it more than the English use it. Okay, so that's what it looks like. Oh, and it's got a flow rate here, like a what do they call it? A uniform velocity profile of 4 feet per second. The other reason that I really like this problem is that this is unlike everything else you do in this class. So I'm going to draw a little line here to show that the water just kind of keeps on going. Okay, now, but this sluice gate can do 2 things. So you can keep it in that position, or you can keep it in this position, where you're like, you know what? We don't want the water to rise. Like we don't want the water to flow. Okay, now you have your reasons. Maybe you want to protect flooding downstream. Who knows what's going on here? And then you've got this on this end. You've got stagnant water. Okay, so this is 1.5 meters. This is 10 feet, not meters, feet, right? The units, the system of units problem is real, and it gets even me. Okay, so 1.5 feet. Okay, so the question is, we want to figure out okay, and I like this problem because it brings in a lot of things, but so this is the given, and the required is we want to figure out the force on the gate. Okay, the net force on the gate. So I guess we could call it the sum of the forces equals what on the gate. Okay, in both situations. Okay. The other thing that it gave you, and I actually made this part up to add to the problem, is that the width of the gate is 1,000 feet wide. So that's into or out of the page. Okay. All right. Let's see. Okay, so how do we do this? Let's see. Let's make this 4 feet per second. Okay, so on the right, hopefully some of you guys are going, well, this is not that difficult a problem. This is a force on a gate, right? It's just that the gate, in this case, has fluid on both sides. So here we go. We've got a velocity prism here because there's no movement, right? So it's just a pressure prism, right? The pressure at the surface is 0, and as we go downwards, it increases with depth. The pressure at the surface here is 0, and as we go downwards, it increases with depth. Okay, so the net force on the gate is one side minus the other side. Okay, so the pressure on this side, okay, well, that's FP, the force of pressure. Let's call it the force of pressure on the left. Okay, well, that's gamma. The height of the centroid, left centroid, because there's going to be a centroid on the right as well. And then the area. Okay, the area left. And this side will be force P right equals gamma times the H of the centroid on the right times the area of the right. Okay, so let's go ahead and solve this one. Okay, so this is going to be FPL minus FPR. Well, I guess in this case, that's what we're solving for. So let's go ahead and say the sum of the forces equals FPL minus FPR. Okay, so sum of the forces equals FPL, that's gamma. Well, we're talking about water here, so that's 62.4 PCF. Okay, HCl, okay, what's the height of the centroid? Well, if we swim up to this and we're looking at this shape, it's going to look like a rectangle. Okay, so I could do my little shape calculations, but in this case, it's just a rectangle, right? So this is the height of it, and the width is into the page. So the height of it is 10, so the height of the centroid is 5 feet. Okay, and the area on the left, that's the area of this rectangle, is 10 feet tall by 100 feet into the page. Okay, so that's the force on the left. The force on the right, well, it's going to be gamma, 62.4 PCF, okay, times its centroid height. Now, this is a different rectangle, but it's still a rectangle. So it's going to be half of that 1.5. So that's 0.75 feet. And then we're going to multiply by the area of this rectangle right here. So that's 1.5 tall, okay, times 100 feet into the page. Okay, so the sum of the forces on the gate, I guess we could call this sum of the forces on the gate. Okay, equals, well, I guess we'll just do some math here, right? So let's see here. We can pull out that gamma. I'll be left with 5 times 1,000, so it's 5,000. 5,000 minus 0.75 times 1.5 times 100. And then multiply that whole thing by 62.4. Equals some really big number. As you can imagine, 304,980. Okay, and we've got feet, so it's a cubic foot. This is pounds per cubic foot, so I'm left with pounds. Okay, so the sum of the force in the gate equals 305 kilopounds. Okay, does anybody have any questions about that before I move on? Okay, because I'm gonna have to delete this line is the problem, because it's in the way. Okay, so this line is in the way. Okay, so we want to compare the forces between these two. Note, it should have been obvious that the force on the gate was to the right. Okay, because there was more water to the left. It was deeper, right? That's pretty much what it boils down to. Okay, so on the right, now we have a different sort of problem. And that is, how do we get the force on the gate? And so what I'm going to do here is I'm going to draw a free body diagram. Well, I'm just going to kind of trace my free body diagram, or my control volume. And I'm going to do it like this. Okay, I'm not including the gate. So it's just a free body diagram, or it's just a control volume of the water without the gate. And the reason for that is because there is a force right here. So all the forces on this, and we have a few. Okay. Oh no, I shouldn't have erased that. Oh well. So the first thing is I've got a hydrostatic force right here. Okay, this is the pressure of the water. Okay, and we just calculated that. Let's see here. Maybe I can kind of real quick get these values. Well, actually, I guess I don't need those values. Okay, so let's ignore that. Okay, so then, so we've got that, and we've got this little pressure going backwards here. And you might say to yourself, well, you know, Wagner, this is supposed to be that formulation only works for hydrostatic. So it works for hydrostatic, or it works in the cases where we have steady flow and the streamlines are perpendicular to the direction we're measuring. So in this case, the streamlines are like this. Okay, so they're all going perpendicular to the direction that we're measuring, which is down. Okay, it's not really perfect, but it's good enough. Okay, so we've got that. Okay, what other forces do we have on this? Well, the gate has a force on the water going in this direction. Okay, so that's force gate on water, GOW. Okay, obviously, really, there is a Y component to it, but we don't care about that, you know, because there's some friction along here. We're not going to worry about that because we're not going to solve this in the Y direction. So there's F, GOW in the Y direction. Maybe we will, you know, we might have to solve that. Never mind. We'll probably have to solve for that too. Okay, there is a weight of water going downwards. Okay. And well, there's also a friction along the bottom here. Ooh, this is getting complicated. I wonder if I wanted you guys to neglect that friction. Give me 1 second. I want to see if I did. This was a late ad. This was like one of my favorite questions. Okay. Yeah, it looks like when I did this, I neglected that. So we're going to neglect this. We're going to assume 0. Obviously, if I gave you this problem, you wouldn't be able to, either I would have to tell you how to get that, or, you know, or basically I would have made a mistake in my formulation. So anyway, so we're just going to, and the other thing is we're only going to do in the X direction because we can't do the Y direction because we can't get this weight. Oh, you know, we can do it. Okay, never mind. The reason we could get the weight, or we could get at the weight, is because there's a normal force right here, and the normal force and the weight basically going to cancel each other, except for whatever this thing holds. So we're just going to ignore the Y direction. Okay, so here's the things. We're going to say force of friction at the bed is 0, so these are going to be assumptions. And that we're only worried about the X direction, only in X direction. Okay. All right, so let's go ahead and solve this. The point right now is I want to do the momentum equation anyway. Like that's what this is all about. Okay, so we've got a velocity here crossing my control volume, and we've got a velocity here crossing my control volume. Okay, so this will be V1, which we know to be 4 feet per second. This will be V2, which we don't know what that is. Okay, so let's go ahead and do our momentum equation. So let's see here. So the sum of the forces in the X plus the sum in of rho VQ. Okay, we only have one in equals the sum of the outs. We only have one out, rho VQ. Okay, and again, remember we have vectors for this X and we have vectors for our forces. Okay, so the first force is this one right here. Right, and the second one is this one right here. Now I know that those two add up to 305 kips. So I'm just going to go ahead and use that number. Okay, this number right here. Okay, because it's the same as what we had over here. So we're going to have 304,980 pounds. Okay. And then what other forces do we have? We've got this FGOWX. So minus F Gauss. Sounds like a rude word. I think that those are all our forces if we're going to neglect this force of friction, okay, which we're going to neglect. Okay. So then let's see here. So now we need to figure out what's going in. So that's all this stuff that's coming in on this side. So that's plus the rho. So that's 62.4 PCF. Okay. Vx, 4 feet per second, 4 feet per second, feet per second. Come on, you can erase. There you go. 4 feet per second. And then Q. Well, we never figured out Q, did we? Okay, well, we can get that pretty easy. So let's give me a little room for an aside up here. Okay, aside. Okay, we can say Q equals V1, A1. So Q is, well, the velocity is 4 feet per second. The area is, well, it's 10 feet tall times 100 feet wide. Okay, so Q is, what's that make it? 4,000? Yeah, 4,000 CFS. Okay, so 4,000 CFS. Oh, and this 4 feet per second was positive, so we want to make sure we make note of that. Okay. So one thing to note is that we get very used to, for our areas, of doing pi d squared over 4. You know, so just, you know, remember that this cross-sectional area in this case is a rectangle. So don't you know, don't get, you know, too kind of used to just doing things in a, you know, the same ways over and over and over again. All right, so then we got this out term. So we're going to say equals. So now we're dealing with this exit right here. Let's see, we've got 62.4 PCF. Okay, we don't know V2, but we can get it from kind of continuity. I can say, well, the Q here, the flow rate here equals the flow rate here. So that means I can write, so I can say Q equals V2A2. And since Q is 4,000 CFS, V2 is what we're looking for. And the area there is 1.5 feet tall by 100 feet wide. Okay, so whatever 4,000 divided by 150 is, that's going to be an ugly number. 4,000 divided by 150, 26. So V2 equals 26.667 feet per second. So a lot faster. And it makes sense. This has a lot more area to flow through. So it can kind of like leisurely move through there. And then over here, it doesn't really have nearly so much area. So it's gonna have to go a lot faster. Okay. Note that that still is going in the positive direction. It still has the same Q, 4,000 CFS. Okay. So notice that this momentum flux is a lot bigger than this momentum flux. And that's just because the area smaller is moving faster. Okay, so let's go ahead and solve these things. I'm gonna go ahead and plug these into my calculator just so I have some numbers here. So let's see here, 62.4 times 4 times 4,000 equals, let's see here, 998, 400. Okay, pounds per cubic feet. We've got feet. No, we've got cubic feet here. So I'm left with, wait, dadgummit, nobody caught me on this. Why didn't somebody say something? Okay, y'all are concerning me. Because I've now made this error several times today and nobody has caught me. Okay, hopefully you're seeing what the error is right now. Okay, the rho is 1.94 slugs per cubic foot and 1.94 slugs per cubic foot. Okay, so if you made that, if I had just done that, I would miss 2 points on my exam. And you know, it's just nickeling and diming. And I don't want to nickel and dime you, but I got to take off if you make errors. So let's let's not make that error. Okay, so we've got cubic feet down here. We've got cubic feet here. So I'm left with slugs feet seconds squared. So a slug foot per second squared is a pound. Okay, so let's do 1.94 times 4 times 4,000. Okay, so that's this is 31,040. That's pounds. And on the bottom, well, I don't have to do the units again because they match the ones on the top. Let's do 1.94 times 26.667 times 4,000 equals 206,936. Oh, that's too many sig figs. We don't need all that. Go to 940. Okay, pounds. Okay, so what you'll notice here is that the opening that gate relieved a lot of pressure. So again, you can almost think of it like a jet. Here's my jet right here, right? So it's almost like it's causing the system to want to go to the right, right? Kind of. So anyway, so let's go ahead and solve this. So this is FGOWX. Okay, so we can plug all these numbers in the calculator. So I'm going to take that number. I'm going to leave it where it is. I'm going to subtract 31,040. Okay, and then we're going to subtract 304,980. And I'll be left with that negative number. We need to make that positive. So that's 129,080 pounds. Okay, so the FGOWX equals 129 kips. Okay, and it's like, okay, so that's cool. That's how much so we assumed the correct direction. So that's actually 129 kips to the left. And so actually the force on the gate, or some of the forces on the gate in this case, okay, is it looks like it's going to be the opposite of that. So is 129 kips to the right. Okay. So notice opening the gate relieves a lot of pressure. Okay. This is not the same answer I got when I solved this for the key, which is very interesting. Well, what do? You know, it's not that far off, but it's different. So there's an error somewhere. I don't know what it is though. That's really weird. Huh. Oh, that's right. I remember. Okay, this was correct. The solution on the internet is wrong. Okay. Any questions? You guys are very quiet this morning, although the trucks in my neighborhood are not. Okay, so I'm going to work one more. This type of problem will be highly, highly unlikely to see a sluice gate. Only because I've never assigned you one. But yeah, so yeah. Okay, so interesting. Oh yeah, okay, so hey Rocky, shush. Anyway, so that's it. Okay. Next problem. Let's go clear my drawing, clear all drawings. Okay, so let's go to same problem set. And I'm going to do this one. It's basically not that different. Trying to think. I think, yeah, let's do. Okay, let's do number 3 because it's like my favorite type of problem, and so I'd like you guys to see my favorite types, because if they show up, then you'll be ready. Okay, so this is number 3 again from that homework assignment, and it says water flows through a contraction. So contraction looks like this. Okay, and then it's got a manometer, so we're going to assume that this is attached. Yes, my Rocky dog. I know. Apparently 2 hours was not much enough of a walk for you. Okay, I need you to relax. We can go outside again in a little bit. All right, so it tells you that this is a 0.1, tells you this is a 0.2, which is really the only places that manometer is helpful for you. It draws it like this. Okay, so when it draws it like that, that means the pipe keeps going. Okay, so these are not jets. This is a Q. And we've got basically somebody has clamped this thing in place using some sort of clamp that's got bolts going through here. Okay. Okay, and the pipe diameters is section 1 and 2. So it says this one right here is 9 centimeters. And this one right here is, I think, 6 centimeters. And the pressure at section 2, so P2, let's go up here with my givens. P2 equals 120 kPa. Okay, which is going to be better for us if right off the bat we convert that to pascals or newtons per meter squared, because that way we won't end up with a units problem sometime later on. Okay, I guess I could have done that with my centimeters, but I didn't. Okay, and then so then there's a fluid in here, which is mercury. So the S of the Hg is 13.6. And there's a height difference between these two of 58 centimeters. Okay. So again, the centimeters is a potential for error because we want to make sure that we don't forget to change that into meters. Okay, so it says assume ideal fluid flow. Okay, so when it says things like that, assume ideal fluid flow, or it says assume inviscid, that means you can use Bernoulli, is what that means, because it means that there's not going to be any friction. Okay, so and then the last thing right here with required is it wants to know the force supplied by the flange. Okay, so the force of the flange. So what's the force of the flange? Let's call that lowercase f. Force of the flange on the everything else. Let's just call it the force of the flange on everything else. Okay, so the force of flange not equals 0, equals what? Okay, so I'm going to do a control volume. Okay, here's my control volume. I'm going to include the pipe. Okay, why? Because you know what? We don't actually need the we don't need the manometer. Okay, because I need the force the flange is putting onto the pipe. Okay, so I guess it's force flange on pipe. Okay, so this includes the pipe. Okay, and so now we've got the force of the flange, which I'm going to assume, I don't know for sure, let's just assume it's positive. That's usually the best policy. So let's assume the flange is pushing to the right. Okay, that's the force of the flange in the X. Let's do the force of the flange in the Y as well. Okay, actually I screwed up when I drew my control volume, didn't I? I actually needed to be at 1 and I needed to be at 2. Okay, so I'm not going to erase that because it's pretty hard to do. But the reason that we need it to be there is because that's where we're going to get the pressures. Okay, because that's where the manometer is. So I'm going to have, okay, so we have to think about our forces. We have to go over these surfaces. So here's a surface. Okay, that one's got a pressure on it. P2A2 is right there. Okay, P2A2. Okay, this top surface, okay, I should do that in blue, I guess. This top surface, okay, on the outside of it, the only thing it's got is the force of the flange in the X and in the Y. Okay, it could be, I don't know which side it's on, so that it also accounts for the bottom. Okay, this front surface here, okay, it's got P1A1, so we're going to do this one. All right, now the only other force that you ever have to worry about once you've gotten rid of all the surface forces is you need to work with the weight here. So there's a weight of the water, which we cannot solve for here because they didn't give us the volume of the water in the pipe. So basically for the vertical, if we were to do the vertical, there's no pressures in the vertical. So basically this would be equal and opposite to the weight. but we can't solve for the weight, so we can't solve for that if they don't give us the thing. So for this problem, like, you're just gonna have to just go, ignore vertical. Okay, and again, I'd have to tell you that on a test. Okay, or you could write this, and if it was correct, you'd get the point. But if it was incorrect, basically this would be an unnecessary stressor for you guys. I will try not to make this error. Anyway, so let's do this in the horizontal. Okay, so in the horizontal, let's do so. And one of the things here is, how do you know what we want to do here is the momentum equation? I asked this again and again on my more organized lectures. And what you're looking for is this a question of forces on a moving fluid? Forces on a moving fluid can only be done with momentum equation. Okay, so we've got moving fluid and we're asking about the force. It's got to be momentum. Okay, so let's go ahead and do it. So we'll say the sum of the forces in the x direction. Okay, we're only going to go in the x direction equals the sum of the ends, rho vxq, equals the sum of the outs, okay, the momentum fluxes of rho vxq. Okay, so speaking of which, I forgot my momentum fluxes. So we've got a momentum flux here, and I've got a momentum flux here. Okay, so this will be v1, this will be v2. Okay, so in the x direction, forces. I've got fx. And I've got pressures. So remember, all these pressures have signs. So I'm going to say P1A1 is positive. So that's this one, P1A1. And then P2A2 is negative, minus P2A2. Okay, now I got to do my ends, plus rho in V. So we're going to start with the one side. So that's going to be V1, and that's a positive number. So let me go ahead and put that positive there. So it'll just remind me that I've taken care of that. And then Q, and Q does not have a sign. So we're just going to put Q. Don't know that we know what Q is. Do we know what Q is? It's not given. So we're going to have to figure out what Q is. Equals, and then the outs. Okay, so we've got rho. It's the same rho for both of them. Vx, or is just V2, and it's positive because it's going to the right. And then Q. Okay, so that's the equation that we're going to use. But we need to think about what do we know and what do we not know. Okay, so let's see. We're going to go through this and say, okay, this is what we're looking for. Okay, P1 is unknown. Okay, A1 we can get from the 9 centimeters. So we don't know it, but we can get that. So we're not really worried about that. So I'm going to go with the check. P2 is given. Okay, it's 120,000. A2 is, well, we know what that is because we got that 6 centimeters. Rho, well, this is water. Did it say it was water? Water. Yeah, water. Okay. Water. Okay, so the rho is known. The rho is known. Okay, as long as we don't make that error. Okay, which I've made twice now. So in this case, let's see, we're in the metric system, so rho is going to be 1,000. Okay, V1 is not known. I don't think, no. Okay, Q is not known. V2 is not known. Q is not known. So we've got a lot of things going on here. Okay, so let's start with what I think is probably easiest. Let's just kind of do our asides. Okay, so let's do the asides. And I'm just going to go kind of in order. Okay, so the first thing is I need this P1. Well, the most obvious way to get P1 is through the manometer. So I'm going to start at P2 and I'm going to work backwards until I get to P1. So here's P2. Okay, so I'm going to go down some distance. Let's call that H. Okay, so I'm going to go the fluid plus the gamma of water times H. Okay, now I'm going to keep going downwards through the fluid until I'm even with this. Okay, so I'm going to go plus gamma mercury times that distance, which is 0.58 meters. Okay, so now I'm over here. And now I'm going to go up. So I'm going to go minus, and I'm in water, gamma water. So I'm going to go up the 58, and then I'm going to go up the H. So 0.58 plus H. That's how far up I went. And that's going to give me to P1. Okay, so let's see. We can say, so P2 is 120,000 newtons per meter squared, plus the gamma of water H. This gamma of water H is going to cancel with this negative gamma of water H. So I'm going to get rid of this one and I'm going to get rid of that one. So I'm going to be left with gamma Hg, 13.6 times the gamma of water, which is 9810 newtons per meter cubed, times 0.58 meters, minus the gamma of water, which is 9810 newtons per meter cubed, times that 58 meters, 0.58 meters equals P1. So P1 equals, we're only a calculator away. Okay. Please interrupt me if any of that was confusing. This to me is a fundamental skill of this class. And it's pretty common. I have students that somehow make it through the class not knowing how to do this. But if you don't know how to do this, you're not going to do well in the class. So, it's just a really good idea to know how to do this. So this is 191,690 pascals, okay, or newtons per meter squared. Okay, note, thinking from a Bernoulli standpoint, the water is moving slower up here because this is a wider pipe. And so when the water is moving slower, the pressure is higher. Okay, so we would expect to have higher pressure here than here. Okay, basically the energy is being transferred from velocity or from pressure at 1 to velocity at 2. Okay, so the pressure goes down, but the velocity goes up. Okay, so now we got P1. That's cool. Okay, so now we now got to somehow get at these velocities. And the problem is I don't know Q and I don't know velocities. I know neither velocities. So I can't just do a continuity, which is what I wanted to do. So I can't do that. So I'm going to erase this so that I have more space to do this. So, but there's a hint here somewhere and buried within this. And the hint is that they said ideal fluid flow. So that hint tells you that you might want to use a Bernoulli equation. So we're going to use a Bernoulli equation here. So what I'm going to do is I'm going to go from 1 to 2, P1 over gamma, plus Z1 plus V1 squared on 2G equals P2 on gamma plus Z2 plus V2 squared on 2G. And one thing to be careful of is these are gamma water, because that is the fluid that is flowing from 1 to 2. Okay. So the first thing I'm going to do, because it makes my life easier, is I'm going to get rid of these Z's because they're the same. Okay. I could either say they're both the datum or I could say they're both the same. Either way has the same effect. So if they're just the same height, then algebraically they go away. If they're the datum, then they just both become zeros. Okay. So now that thing that I was just talking about, where I said P1, the pressure at 1 is higher. So basically the energy at 1 is mostly pressure, and the energy at 2 is mostly velocity. So I'm showing mathematically what I just said in words. Okay, so this is going to be 191,6. Oh, how did that happen? Okay, 690. Okay, it's a little bit of a rounding there, but it's fine. Newtons per meter cubed over 9810 newtons per meter squared plus something over 2G. So 2G is going to be 2 times 9.81 meters per second squared equals, and I don't know V1 squared, P2, which was given as 100, come on, man, 120,000 newtons per meter squared over 9810 newtons per meter cubed plus, okay, again, 2 times 9.81 meters per second squared. Two unknowns. Okay, when we have two unknowns, we get annoyed because I can't solve this problem. I can't solve this. And so, I went straight into Bernoulli, which seemed like a good way to go, but I also need continuity. So I need two equations because I have two unknowns. So in continuity, I can say V1A1 equals V2A2. Okay, and this is another equation, and I know these areas, so I can get at this. Okay, so let's see here. V1 times the area, which is pi, times the diameter, which is 9 centimeters, 0.09 meters squared, divided by 4, equals V2 pi 0.06 meters squared over 4. There's a closed parentheses on there, which I can't fit. Okay. The easier way to do this always is if you notice these ratios, because all these pi's over 4 go away. You notice that one side is 1.5 times the other side, so it's 3/2. So you square that 3/2, and you'll get 9/4. And we know that V2 then equals 9/4 of V1, or if you prefer, V2 equals 2.25 V1. Okay, you can also just solve this if you wanted to. But I recommend seeing that relationship. It's a lot easier, a lot faster. Okay, so over here for V2, I'm going to put 2.25 V1. Okay, we're going to not forget to square that 2.25. That is the most common error in this class. And we'll have a V1 over here squared. Okay, now we've got one unknown and we can solve this. Okay, so I'm going to go up here and we're going to go ahead and solve this. Okay, so this is just calculator work. See, how are we on time? I got 10 minutes, so we can finish this. 191,690 divided by 9810. Okay, 19.540. 540 meters. Minus, I'm going to subtract off this one. 120, 123 divided by 9810. Got fingers that are not functioning today at 0.232 meters. Okay, equals. Now I'm going to square this and I'm going to subtract off that 1. So it's going to be 2.25 squared. Okay, 5.0625 minus 1. So I've got 4.0625 V1 squared divided by 19.62 meters per second squared. Okay, so this should all work out. So 19.540 minus 12.232 times 19.62 is that number divided by 4.0625, and we're going to raise that to the half power, and we get V equals 5.9409 meters per second. Okay, and if I plug that down here into this one right here, I can get V2. So I can just multiply that number by 2.25, and I get V2 equals 13.367 meters per second. Okay, so now if I go up to my original equation here, I've got P1, I've got V2, I've got V1, and the last thing I just need is Q. Okay, so we get Q by doing V times A. So it doesn't matter which velocity I do as long as I do the correct area. So we'll do Q equals V1, 5.9409 meters per second, times the area here. So that's going to be pi times 0.09 meters squared over 4. Okay, I know this is getting awfully sloppy. I wish I had more whiteboards. Okay, so let's just kind of erase all this. So this becomes Q equals whatever that number is. This times pi times 0.09 squared divided by 4 equals 0.037794 cubic meters per second. Okay, so then all we got to do is plug and chug all that in there, and that'll give us our answer. Okay, I guess we might as well finish it. So let's go ahead and do that. Fx plus P1, which is 191,690 newtons per meter squared, times the area, which can be pi 0.09 meters, squared over 4 minus P2, 120.123 newtons per meter squared, times pi times its diameter, which is going to be 0.06 meters squared divided by 4. Okay. And I'm going to have to create some space here. Okay, plus rho, which I've now screwed up multiple times today. So let's focus here. The rho here is, is 1,000 kilograms per meter cubed. Okay, V1 is, let's see, what is V1? Oh, it's 5.9409 meters per second. Okay, Q is 0.037794 cubic meters per second. Cubic meters per second. Equals rho 1,000 kilograms per cubic meter times V2, which is 13.367 meters per second, times Q, which is 0.037794 CMS. Okay, so this is a doozy, or it has been a doozy. All right, so let's go ahead and solve it all the way, and then we will be out of time. But hope if you have any questions, we will have enough time for that. Okay, nobody said anything for a long time. I don't even know if I'm all alone. Okay, so we'll do this. So 191,690 times pi times 0.09 squared divided by 4 equals 1219.5. Okay, and let's check our units. Meter squared cancels with meter squared, so we're left with newtons. Newtons minus 123 times pi times 0.06 squared equals divided by 4 minus 339.29 newtons. Okay, same units going on there. Plus 1,000 times 5.9409 times 0.037794 equals 224.53 newtons. Again, let's see here. Meters cubed cancels the cubic meters there, so I'm left with kilograms, meters, seconds squared. Okay, so that's a Newton, right? Okay, and then equals, on the other side of the equal sign, we've got 1,000 times 13.367 times 0.037794. All these numbers, we're kind of getting away from, what we're doing here, but it's okay. 505.19 newtons. Okay, so let's go ahead and, F of X. Notice that in this case, the strongest force here is this one. The 12 point, the pressure on the right. I guess it's kind of what's driving the flow. So anyway, so let's get an answer here. 1219.5 339.29 plus 224.53. Enter. Times -1 at 505.19 equals, so we get negative 599.55 newtons. So FFX equals negative 600 newtons. Okay. That's with 3 sig figs. I don't know, you gotta feel pretty good when you end up with a nice clean number like that, or you gotta feel real bad. I don't know which it is. Questions. I kind of worked that one a little quick. But we've seen quite a few of these now with the manometer and the continuity. So any questions?
So basically, if we need to find a force, then we're going to use momentum. Like
yeah, almost always. I can't think of a case when that wouldn't happen. I mean, if the fluid wasn't moving, then you would find a force just using like hydrostatics.
Okay.
You know, but if the fluid is moving and you need a force, I can't think of any time when that would be anything other than I can't think of it. Yeah, to me that's always going to end up being momentum.
All right.
Any other questions? Okay, well then I'm going to log off. I'll stop recording and we will call this a day. So again, take care of yourselves, and I will see y'all. Today's Thursday, so have a nice weekend. Hopefully the weather continues to be beautiful. All right, see you guys.
All right, thank you.
Later.
All right, bye y'all.